Good morning, everybody. That was pretty lame. Come on. Good morning, everybody. So much better. So it's awesome to be back at Ignite here in Chicago. Last time I was here for Ignite was 2015. Anybody here for that Ignite? Yeah? You remember my session back then? It was awesome. So anyway, welcome to Azure Innovations. My name is Mark Russinovich. I'm CTO for Microsoft Azure. I'm also a technical fellow, and now I'm also the Deputy Chief Security Information Officer for Microsoft Azure. My goal is to get as many titles as I can before I retire. So this morning, I'm going to take you behind the scenes of some of the innovations that we've got under development and just released in Azure, to give you a view across the spectrum of 3 different areas for how we're trying to push the envelope for innovation in our infrastructure and our cloud-native computing application layers. I'll talk first about inside our servers, talk a little bit about some of the hardware acceleration that we've got developed there, then talk a little bit about what we're doing in cloud-native computing to run those workloads on those servers, and then finally I'll talk about confidential computing, which is the future of computing. So let's go ahead and start by talking about servers. And I'll start by just framing what I'm going to cover in the context of traditional IT infrastructure, which is the vast majority of today's IT infrastructure still on premises. The standard server with the standard storage network stacks that are running on the hosts, virtualized ideally, that are talking to the hardware. In some cases, the hardware is directly attached to the virtual machines, but in many cases, there's compute that happens in the host. Now, if you take a look at the modern cloud architectures, it is focused on disaggregation, pulling that computing that is supporting those virtual machines, the storage and network aspects of computing, off onto an offload card. This accelerated offload card in Azure is called Azure Boost, and we announced it, I think it was last Ignite in Seattle, the first Azure Boost. Just to be clear, we've been disaggregating parts of our infrastructure for a decade. Our first network accelerated offload we released in 2014. And that was Azure Accelerated Networking, which gave us high throughput. It wasn't on a separate offload card, but it was offloaded into FPGAs, much like the offloads that we still have on Azure Boost with FPGAs. Here's a picture of today's Azure Boost card. I'm going to talk a little bit about what's going on inside of this in the next few minutes, but you can see a couple things there. There's 2 network adapters there. Those are Ethernet 200 gigabit ports, or 100 gigabit ports each, for a total of 200 gigabits coming off the card. That large block in the middle is the FPGA, and then the smaller block to the right of that are ARM cores running Linux. This is, in fact, it's Azure Linux running on those ARM cores. So I never thought I'd be saying that in 2014. That in 2024, I'd be saying Azure Linux is running on our offload card. But here we are. Now, we're using Azure Boost for a few things. One of them is to accelerate remote storage processing. So you can see here the before. We started offloading remote storage. You can see the traditional architecture, like I mentioned, virtual machines talking through SCSI, those storage packets, those blocks going off into the Azure software stack through Hyper-V and down to remote storage. With Azure Boost, the after picture looks very different. Now the virtual machines are talking through NVMe interfaces that are projected up from Azure Boost into the virtual machines, and that traffic is going through the accelerator off into the remote storage, whether it's an Ultra SSD disk or an Azure Premium SSD. One of the things that we get out of this architecture that we've developed with FPGAs is the ability to update it while the fleet is live. So rather than waiting for new revs of the hardware, we can actually optimize the acceleration code on the FPGA to bring higher speeds and feeds. And so just one example, when I announced Azure Boost last year, we supported 650,000 IOPS, cloud leading at the time, on 2 sockets. Today, now we support 750,000 IOPS on 16 sockets. And the 16-socket support we brought into the picture to support our M-series virtual machines, which some of you have seen me demonstrate, like running Task Manager on 1,700 cores. Those are the M-series. And then we've also been able to dynamically upgrade the throughput from 12.5 gigabytes per second to 14 gigabytes per second. We've also been using Azure Boost for local storage acceleration as well. Again, in the traditional architecture of IT infrastructure, you see the virtual machines talking SCSI through the virtualized stack down to the SSDs. Now what we're doing is using multifunction SSDs, projecting those SSDs right up into the virtual machines through Azure Boost, controlling the security of that connection, and that allows us for this very high throughput access for virtual machines to local storage. Again, by accelerating local storage, we've gone from 3.8 million IOPS support on a single large virtual machine, E-series virtual machine, to 6.6 million IOPS. It seemed like just yesterday that Jeff Woolsey, some of you might remember him, was showing, wow, 1 million IOPS on Azure Converged Infrastructure for Azure Stack HCI was back then. Here we are now talking about 6.6 million local storage IOPS on a commodity virtual machine in the public cloud. We've also gone from 17.2 gigabytes per second to 36 gigabytes per second, over doubling the amount of throughput now we offer on those local SSDs. And one of the benefits we get out of this comes in the context of live migrating virtual machines that have large amounts of local storage. One of the challenges we've traditionally had, because of the slow throughput we were getting off those SSDs, is the transfer times and the brownout times were extremely long, and the blackout times were extremely long if you had a very storage-intensive workload. So what I'm going to show you here is a demo of live migration of a very storage-intensive application. Now, this is not going to actually show the virtual machine live migrating. We're going to actually just live migrate the local storage, and you're going to see the blackout of the live migration. And then the virtual machine is just going to continue running on the local system, so you can see the performance continue afterward. So this is a little performance testing tool that's just going to drive TPC SQL queries. I'm going to go ahead and kick that off, and you can see it's driving about 1.8 million transactions per minute off of these local SSDs. I just kicked off a live migration, and then you can see a little blip as the live migration of that storage starts. This is the brownout period where you can see the throughput is dropped, and by the way, every one of those clicks is 10 seconds. This is just sped up so that we're not waiting while that entire SSD is being live migrated. And then we come to the end of the live migration where we've caught up with the virtual machine. There's a blackout you just saw, lost the RDP connection. Now we're back after the blackout, and we're back to normal processing. And here's 𝗲𝗲 showing the transactions per second. It's about 30K transactions per second. You can see the entire time reading it right up into the brownout, small blackout blip, and then we're back and running. So now we're able to live migrate even virtual machines with large amounts of local storage because of Azure Boost. We can do it very efficiently and get these low blackout times. So let me talk a little bit about what we're doing in networking. That's a look at storage, remote and local storage. Let's talk about Azure Boost and remote, so networking. One of the benefits we get out of Azure Boost and networking is, like I said, 200 gigabits per second because of Azure Boost's network adapter support, 400,000 connections per second. And then we've got now redundancy because we've got 2 links coming off the card. They're going to different links in the top-of-rack router, so now we have more resilience there, actually 2 routers. So now we can actually service a top-of-rack router. One fails, and we don't lose connectivity to those servers. But a big thing that we're getting out of this architecture of offload is better servicing times, where instead of when we want to service the network stack, we don't have to bring down the entire server, bring down the entire hypervisor, and cause this big blackout, or even reboot the virtual machines. Now we can do it very quickly on the Boost offload card. The way that network driver updates happen in Boost now is that on Boost, there's a network agent there that is managing the flow states coming off the virtual machines. When we bring up a new network agent, and get it, well, so the old network agent leaves its virtual flow states in memory, in RAM, on the Azure Boost card, shuts down, the new one starts up, and there's a handoff of state. And that means there's no copying of state, there's no serializing of state. It's basically in-memory transfer of all that state. And this is actually what we're going towards, a journey that we started with something called Virtual Machine Preserving Host Update that I talked about close to 10 years ago. We've been evolving our update infrastructure, even into Azure Boost, of doing this memory transfer, so you never have to serialize or deserialize when you're updating components of the operating system. We can do this not just with the network agent, we can do this with the entire network stack processing on Azure Boost as well. The blackout times vary, depending, or the brownout times and blackout times vary. But what I'm going to show you here, a quick update, is actually a demo of updating the network agent on that Azure Boost card. So here, I'm going to run a little benchmark tool that just is showing number of connections per second, and this is where we're going to see the effect of that network update. Here's the version of the agent that's currently installed. Now update to the new agent, so this little script does that. And you can see that there's really no impact on that throughput there on the left side. Now I take a look at the new version of the agent. We can see the new agent is now up and running. Now, how much impact did that have on network capability for the virtual machine? Well, there's two aspects of it, gray out time and blackout time. And the gray out time is about 100 milliseconds. The blackout time is about 250 milliseconds. Gray out means, it's the term we came up with to mean that the network isn't supporting new network connections, but it is still processing the existing flows, versus blackout time means the whole network traffic has stopped. But you can see 250 milliseconds now while we're doing a full update of our network stack, which is basically invisible to the vast majority of applications. And so now we can service our fleet much more efficiently, bringing new capabilities like the ones I showed you, improving throughput and connections per second on the networking stack, while the virtual machines continue running happily along. Now, another thing we're doing with offloads, it's the same philosophy as Azure Boost, but a different implementation. If you take a look at software-defined networking, it consists of lots of rules and lots of processing of those network packets and network connections. Some of the things that the SDN stack has to do, and we implement this SDN stack in something called the virtual filtering platform in Azure, which is inherited from what we had in Hyper-V and a Windows Server, is process things like virtual network rules. What are the security rules for what ports are accessible? What are the network ACLs and routes? As well as things like billing and metering. These things can be extremely complicated, especially for applications that are processing millions of flows. And the kinds of applications that do that are commonly network virtual appliances. So what we're doing, and there's other kinds of workloads that need high amounts of throughput coming off of our remote services like Azure Storage. So one of the things that we're doing, instead of implementing the SDN policies on Azure Boost, is offloading those completely to a disaggregated architecture. You can see this is DPUs, like you saw Satya announce, data processing units that we've got in an SDN appliance. And that's a picture of the back of the SDN appliance right there. There's six DPUs in that SDN appliance that can drive a huge amount of throughput and a huge amount of connections per second, coming from anything that's talking through it. One of the actual use case scenario, and by the way, we're also building a smart switch, which is built on top of our SONiC software-defined networking software stack that we developed in Azure and contributed as an open source foundation, something called Dash that supports these DPU offloads on top of SONiC. But if you take a look at one of the scenarios that this supports for us is something called floating NIC, or floating network adapter. You don't even need now to create a virtual machine to support the processing of SDN rules. You can simply create a NIC and say, these are where my SDN processing is happening. Connect that NIC with its IP address to something external, and then all the packets flowing through that get those rules processed, like private link or other kinds of features. We actually got requested by a major AI company that needed extremely high amounts of throughput to back-end storage for their AI training. I can't tell you the name of that company, but it starts with an O. That's all I'm going to say. And they wanted huge amounts. You can see 1.6 terabits per second of throughput to back-end storage. And we could deliver that with this SDN appliance. But the other thing that you get, not just for this kind of remote connection from a different infrastructure into Azure, is something called accelerated connections. Let me show you a quick demo of that. With accelerated connections, I've got a virtual machine here. This virtual machine's network adapter, its NIC, we go click on it and take a look at its properties, we're going to see that it's an accelerated connection network adapter. That means that the SDN for it is offloaded to the SDN appliance. And I've got a tool here called 𝗦𝗲𝗃, which is going to drive connections per second, among some other things. Up in the top right is the connections per second here. And you can see that the connections per second is close to 1.5 million connections per second, which is a huge achievement to achieve. And by the way, this is completely scalable. If we want more, we just add more DPUs to the SDN appliance, and we can scale that out arbitrarily. So you're going to see us scale this out more and more as we get more and more demand for even higher connections per second. OK, so that's a look at our servers. Now I'm going to go into the software layer of compute on top of it, because we've got a lot of cool innovations in that area as well. One of them is the introduction of AKS Virtual Node v2. If you're familiar with Azure Kubernetes Service and Virtual Node that we introduced about 5 years ago, it had some limitations. You couldn't get basically fully native Kubernetes capabilities off of those virtual nodes. With Virtual Node v2, it looks exactly like a standard node in a Kubernetes cluster. We believe the future of the cloud is serverless. And Azure Container Instances is our serverless container offering. We actually were the first public cloud to offer serverless containers with ACI. And we've been continuing to innovate ACI since its introduction. So one of the things that you've always been able to do is go and connect virtual nodes in AKS to ACI. And that allows you to kind of scale burst out, or even run your infrastructure completely serverlessly on top of ACI. One of the things that we've done just recently, and we announced this today, is standby pools for ACI. Many workloads are very bursty, and they need a large amount of capacity kind of ready for them to scale up to the demands that they see, and then maybe scale back down. So standby pools allow you to create these standby pools with standby pods that are ready to go, and then as you start to scale out your workload, these pods just get assigned to your workload. I'm going to show you a demo of that in action. In fact, I'm going to show you a pretty cool demo. Wanted to really stretch this, because some of you come to expect that these talks are going to be like huge demos. So how about if we create 10,000 ACI containers and see how long that takes us? 10,000. So we kick off this on the left side, or on the right side. We're just going to take a look at the current time. You can see 6:44, 1844. On the left side, we're going to kick off scaling 2,500 pods each of 4 of these groups. And what we're going to see now is, as we watch those pods spin up, is first they're a little slow as they start to spin up. That's the count there. The ready count is on the left, 51 out of 2,500. So there's deploy 1, 2, 3, 4, or 2, 3, 4, 5 are the numbers. You can see the ready counts for each of them, and then you can see on the right side the available counts, another way to see it. They're all trying to shoot for 2,500. And here we go. Now they're really launching up, taking advantage of that standby pool. And what this is going to allow is for those kinds of workloads, especially workloads that are unpredictable, especially those kind of multi-tenant workloads where you want to spin them up, because that's one other aspect of ACI, is that they're hostile multi-tenant safe, meaning you can put 2 different customers in 2 different ACI pods and isolate them. So here we go. We're coming up on the 2,500 across all 4. And there we go. We just hit it. 2,500 across all 4 of those deployments. Oh, there we go, the last bit. And then we get the count, the current count, 2,500. So we got 10,000 pods. You just saw it happen, launched. And now we get the time. And it took about a minute and a half. So 90 seconds, roughly, to get to 10,000 containers launched from 0. So that's, and you're free to clap at any time if you like. So the other advancement that we're making with ACI, we're also announced today, is the introduction of M groups. So ACI, if you're familiar with it, allows you to create single instance, effectively, ACI containers and manage them one by one. Not very efficient, and missing a lot of the features that a lot of our customers love in things like virtual machine scale sets, where you can get spreads across availability zones, you can do rolling upgrades, you can get this kind of flexibility to manage the thing at massive scale. So that's what we've done today with ngroups, is effectively have a scale set concept for ACI containers. They're called ngroups, and this means that when you say, hey, I want an ngroup, foo, of the containers, I want a count of 3, I can spread them across zones, and if one of them fails, like we have a failed one, what ACI ngroups is going to do is automatically do a restart, so it's got health built into it as well. So this is the future of serverless, and you see us fleshing out the underlying infrastructure to really support any application being able to run on serverless containers. Now, another aspect of containers is what we call micro virtual machines. And it was build of 2023 that I introduced in this version of this talk, something called Hyperlight. Was anybody there to see Hyperlight introduction? Nobody was there? It's kind of sad. OK, well, so let me tell you what Hyperlight is. Hyperlight was the missing piece that we had for really isolating very fine-grained, lightweight little pieces of code. And you might think, well, that's for containers, the thing in the middle. Well, containers actually have a sizable footprint. And if you've got something like a user-defined function inside of a storage service, or you have something that wants to process network traffic on the edge as it comes into your service, you need something much lighter weight. And it needs to be hostile multi-tenant safe, meaning we need to be able to put customers side by side in these things and make sure that these things are completely contained inside their sandbox. So we call these micro sandboxes or micro virtual machines. And one of the things that we announced, and this was kind of just one of the people that I work with in Azure came to me one day and said, hey, look, I can use the Hyper-V APIs to go create a VM that has no code in it, except for this tiny piece of code that I've just loaded into it. And I can launch it in literally microseconds and shut it down in microseconds. And so, bing, here we are. We've got a micro sandbox that we're going to call Hyperlight, hypervisor isolated micro VMs. And here's me introducing it, build. Here's the announcement just from last week, November 7th, introducing Hyperlight virtual machine-based security. And we've open sourced it. And it not just works with Hyper-V, it works for KVM as well. So, we're contributing this to CNCF. So this is actually want to raise all boats, give micro virtual machine technology to everybody through this sandbox, and Hyperlight is the way to do it. And we're announcing something called Azure Front Door Edge Action. So Azure Front Doors are Edge Front Door Gateway service. A lot of traffic comes in from on-premises, flows in through Front Door, and this is where we can do network processing on that traffic as it comes in using these sandboxes in a very lightweight manner. So I'm going to show you a quick demo of that. And what we've got here on the left side is the code that we're going to run inside the Hyperlight VM. This code is just going to create a thumbnail of an image that's given to it. This is a WebAssembly piece of code written in C++. I apologize for that. On the right side, the Hyperlight code's all written in Rust, which is as it should be. So what you see on the right side is the code that is actually going to call that micro VM, passing it the image through a function pointer. And this is a WebAssembly piece of code. It's just got one entry point, which is this crop image. And there you're going to see these debug prints that we're going to see in a second, creating the Hyperlight sandbox, to show you that for every one of the images we give this, there's a new micro VM being created to process that image so that there's no contamination across processing of images. And so here we're going to go to the web UX, upload a picture. On the right side is the debug output that we just saw. And then you're going to see there that what came out successfully created a micro VM in 1 millisecond, loaded the WASM runtime, loaded the Edge Action module, and executed it. Now we're going to do another one just to show you that it is going to be a brand new cropped image. And this is TechEd 2009. Anybody there? Anybody got that one? Yeah, a few people. It's cool to see. And so you can see now on the right side, it created a brand new micro VM, again, just in 1 millisecond to run that additional cropped image. So that is a tool that you're going to see us spreading throughout our infrastructure, because it's just so useful to just be able to run these tiny pieces of code that you can provide to us that we can run in a secure way next to your data. All right, so let me switch over and talk a little bit about Azure incubations. I've got an Azure incubations team that formed, again, about 9 years ago, and it formed accidentally. I had a couple of technical assistants that we were trying to think about the future of cloud-native computing. Well, actually, before even thinking about that, one of them came up with this idea. He said, you know, what Kubernetes is missing is an autoscaler that's really flexible, where you can have autoscaling rules based on any kinds of metrics. And I said, that's really cool. Let's go and build that out. So he built it out with the other technical assistant, and it's called Kubernetes Event-Driven Autoscaler. How many people have heard of that? So yeah, a few of you, some fans, woot. So 𝗬𝗲 came out of that team, and 𝗬𝗲 became we submitted that to CNCF. It graduated in 2023 to become a graduated CNCF project. But then we're thinking about the future of cloud-native computing. They came up with this idea that we eventually fleshed out into what's now called DAPR, the Distributed Application Runtime. I'm really thrilled because we submitted that to CNCF as an incubating project in 2019, 5 years ago almost exactly, and last week it graduated. So now this is a graduated CNCF project. Graduation means it's a mature project, maturely governed, lots of people use it, lots of enthusiasm and activity with it, and I think it's like the 6th most active project in CNCF. Now, we've contributed some more. 𝗬𝗲𝗀𝗀𝗃, it's a container patching application or project. That's also we contributed to CNCF, and we've deployed this inside of Azure now, inside of Azure Container Registry. And for Microsoft itself, we're patching literally millions of containers a month using our 𝗬𝗲𝗀 technology we developed and incubated. But I'm going to talk about a couple new ones today. One is called Project Radius, and one is called 𝗬𝗲𝗃. Now, Project Radius, let's talk about that one first. So one of the things, talking to customers, is that as Kubernetes took off, a lot of them focused their cloud-native strategies on top of Kubernetes. Kubernetes, it's not really a serverless infrastructure. It's a control plane. It's a separate control plane from cloud control planes. And the way that you deploy applications to it has you merge the application with the infrastructure. A lot of people find it so complicated that what we see as enterprises building abstractions on top or templates that they give out to their development teams. We want to make it easier for developers and architects to craft those applications, not have to worry about infrastructure, and yet let a platform engineering team figure out how to implement security and compliance and cost management. And so that's what Radius is aimed at. Radius lets you define an application of resources that connect with each other. And that application you can make cloud portable, or you can tie it to particular resources in a cloud or a Kubernetes, and then hand that off to a platform engineering team if that's the way the organization's structured. And that platform engineering team creates what are called environments for that application to land on. Those environments have what are called recipes that bind resources to the infrastructure. And the recipes are where the platform engineering team can implement things like security. This database needs to have private link on it. This front door needs to be inside of this virtual network. It also is where they can do cost management as well, and they can do right sizing for the application. What you get out of Radius when you start to use it is you get that collaboration between the development team and the platform engineering team. You get these recipes that can be reused and customized. You get an application graph because you can see all the resources in your app and how they relate to each other. And then you also get cloud portability or cloud neutrality if you want it. So just to give you a little idea of how this looks in practice, this application here, Internet Gateway, front-end container, back-end container, the front end talks to Redis cache for caching, and the back end talks to a Mongo database. You define this application. This is basically a cloud portable application because we're using open source components where you can find open source services, managed services on all the clouds. And you can also bring it yourself with the container. So you want to deploy this on premises? You deploy it onto a Kubernetes cluster, and you specify the containers in your recipe to launch the Redis cache or the Mongo database. And you do that however you want it configured with your recipe. You want to take and deploy that same application to Azure, and you have recipes for the Azure landing zone, the Azure environment, that connect it to Azure versions of those services. And then finally, you want to deploy it to AWS. You've got an AWS recipe. But where Radius is going is more than just Kubernetes. I want to tie it back to ACI and our view that the future is serverless. And that's what Radius is going to enable, because it will let you take the same application and deploy it to Kubernetes or deploy it to a serverless infrastructure. And the first infrastructure we're targeting is ACI and ACI N groups. So the incubations team worked closely with the N groups team to make sure it would support ACI. And what we've got here, a ratified application, an environment specified for it in Azure that's container instances. And then when you deploy it, you get some resource groups with those resources deployed. But you can take that same application and deploy it to Kubernetes. In fact, that's what I'm going to show you right now. This application that I'm going to show you is the Finos TraderX application. So Finos is an organization, consortium of banks that have gotten together to define standards for the banks and drive forward cloud-native innovation and security compliance for the banking community. They've got reference applications. This one's called Finos, and that's actually a picture from there, the TraderX docs, showing this application that consists of representative microservices in a financial application. You can see there's 7 or 8 of them. So we've ratified this application, meaning we've defined this. Oops. We've defined this in Radius. So let's go take a look at that Radius definition. So this is the app definition there we're taking a look at. And then we've got 2 environments, the ACI environment and an AKS environment for a Kubernetes service, where we can launch it onto a Kubernetes cluster. You can see on the right side, it's Kind Kubernetes, on the left, ACI, and then we're going to launch both of them using rad deploy, specify the environment that they're targeted at. The -W specifies the target environment that we have recipes set up for in Radius to do the appropriate creation of that infrastructure. And then now you can see both applications have deployed. We can see the resources that were created in Radius. We can take a look at the app graph and see the connections between the front end talking to the database, or the web app talking to the database. And the same thing is what you see on the AKS side. They look exactly the same, that one is running on ACI and one is running in Kubernetes AKS pods. And now here's the Azure resources for the ACI version, and you can see now the container instances there on the right side and the N groups there on the right side. So what we've just done is had this application, fairly complicated, not web plus database, but microservice-based, real app, ratified it. And by the way, it took 1 day to ratify that app, converting the Helm charts and Kubernetes manifests to Radius, and then got this running on 2 infrastructures. All right, so let me talk about the next one. 𝗲𝗬𝗲. Now, 𝗲𝗬𝗲 is aimed at another problem that I saw with, especially talking about edge and bringing up edge infrastructure and digital twins. This problem of, as resources start to get provisioned, you want certain workflows to happen. Like when this thing's ready, then we need to go install Kubernetes on it. When Kubernetes is ready, then we're going to go deploy apps on it. When those apps are deployed, then we're going to do something else. Digital twins are graphs of objects that state changes. You want triggering reactions. Now, the problem is that the way that people write change detection architectures today is really cumbersome. First of all, many systems only allow you to poll, so you have to sit here and ping over and over again. Some of them have change feeds that you got to process, but sometimes you need to poll and change feed, merge those together. And then finally, some of them have streaming that you need to merge into it. And then the logic that you put on top of that for, did this happen? Has this thing not happened in 30 seconds? Very complicated, very brittle. 𝗲𝗬𝗲 is aimed at simplifying that by allowing you to define a continuous query in the Cypher language, which is Cypher graph query language. And that standing query then, when it's satisfied, You specify what you want to have happen, whether it's execute a webhook, send an event into event grid or event hubs, do a signal R invocation. And the way that you get data into 𝗲𝗲𝗲𝗲 is through change feeds. And it supports open source change feed standard called the 𝗲𝗲𝗲𝗲𝗲, so you can plug in just about anything into Radius. And you as a developer, if you've got a developer doing this, just has to do the query, and they're done, because 𝗲𝗲𝗲𝗲𝗲 takes care of the rest, looking at the change feeds, seeing when the query is satisfied, and then invoking the reactions. So I've got a quick demo here, and this is 𝗲𝗲𝗲𝗲𝗲 running a trivia game. And this trivia game, the UX is completely driven by 𝗲𝗲𝗲𝗲𝗲. So if I go look, you can see here, for each panel, this is the 𝗲𝗲𝗲𝗲𝗲 standing query, which is just like a database query, except it's a graph version of it. And that's it. The UX is updated based on the results of that query in real time. As it changes, the UX changes. So the developer, to create this application, simply created these 3 standing queries for each of those panels, or 4 standing queries. And you can play with 𝗲𝗲𝗲𝗲𝗲 right now. So here's a QR code if you want to go. And this is trivia. So the goal is answer these questions as fast as you can, and you'll show up on the leaderboard if you do that. So let me have to exit that presentation and open the. Where's my mouse? Oops. So what you're doing right now is, oh, no, I don't want to do that. No, stop. Ah, OK. OK, well, this is not. Anyway, so I got foiled by the edge setup there. But you get the idea. What's happening is you're going to see a UX that's completely driven by 𝗲𝗲𝗲𝗲𝗲. And so this is the future of change detection, open source, contributed to CNCF. Go to the GitHub repo, and you can start to play with it. All right, finally, I'm going to conclude with a look at confidential computing. Now, confidential computing, how many people have heard of that term, confidential computing? So quite a few of you. And 10 years ago, nobody would have, because 10 years ago, it wasn't a term. In fact, we've been working on this for a long time that I'll talk about in a second. But what is confidential computing? It's completing data protection through the 3rd stage of the data lifecycle, which has been missing up to now. You encrypt data when it's at rest. You encrypt data when you're transmitting it. Everybody uses TLS. But when you get the data into the server, it's there in the clear. It's exposed to the hypervisor, the host operating system, the application, the DevOps person that's accessing that server. Even physical data center people can access potentially that data in the clear. So confidential computing is aimed at protecting that data, and it does so with something called a trusted execution environment, or TEE. And the TEE has a few capabilities. One of them, it's defined by hardware. So the hardware creates an encrypted black box that the data can be put into, along with some code. And that data is encrypted on the outside. What the TEE does, the code in the TEE does, is ask the hardware for what's called an attestation. This is who I am, presents that to a key release service or another application that then verifies it, says, yep, you're trustworthy and you're protected. I'm going to give you a key that will allow you to decrypt that data. Now the TEE, code in the TEE, can decrypt that data and process it, do ML on it, do analytics on it, and know that it's fully protected by the hardware from the hypervisor, from the host operating system, from anybody else outside of the TEE. And we've been working on this, like I said, for 10 years. And in 2015, the term confidential computing, we coined it with a paper that we published back then. But we've been developing services and bringing confidential hardware into our cloud. Here's a look just to show you that we are the most advanced down this path of confidential computing of any hyperscale cloud. And we've also been working on fleshing out the full story for confidential computing. You saw Satya talk about integrated HSM. That's a key part of our confidential computing story. What that does is allow us to protect keys all the way from real hardware HSMs or replace those hardware HSMs in our infrastructure with integrated HSM, all the way to the servers, keeping them effectively in an HSM the entire time through our integrated HSM technology. Now, I just had to, well, actually. So the VMs never see the keys. They can just use the keys. So this is a key part of cybersecurity strategy. Now, this video, while it's playing, I'm going to show you, I brought my Gen 11 server here with me. This is our Gen 11 server. This is what we're deploying, and this is the hard integrated HSM here that you're seeing in that video is right there. This is the slide-in card for it, the security card. These are the processors, the sockets. These gold here you can see is the liquid cooling, cold plate liquid cooling on the Gen 11s. And by the way, they really looked at me funny when I was using this in Starbucks this morning. But I love it. So now let me talk about what we're doing with confidential AI, the next steps, which is a killer application that is confidential GPUs. We've worked with NVIDIA to bring confidential H100s to market. And we've launched a confidential OpenAI Whisper service. This OpenAI Whisper service means that your text, your speech, is encrypted from outside of Azure all the way into the GPU, into the model, transcribed, and then the transcription comes back to you encrypted. Let me show you a quick demo of that in action. And so here we're going to go create a confidential Whisper inference endpoint. So I'm going down to Whisper, provisioning it, and then one of the options that we're going to see is standard or confidential. So we pick confidential. Now we've got our endpoint set up here, and I've got a web interface here.
I'm excited to announce that 𝗦𝗲𝗀𝗀𝗀𝗀 is the recipient of last year's Russinovich Clean Desktop Award.
So 𝗦𝗲𝗀𝗀𝗀𝗀 won this Clean Desktop Award last year. Very controversial. If you want to hear more about that controversy, come to our session tomorrow. But here what I've done is upload that piece of text, and you can see this came back to the web app, and the web app ensured that it was talking to the confidential Whisper service through the attestations from our attestation service, ensuring that nobody can see that text or grab that speech, because it went right into the OpenAI model and came right back. So that's the future of confidential AI inference. We've also excited to announce a confidential clean room service that allows customers to bring their own data sets together, perform computations on them, analytics or AI training, if they want to, or fine-tuning, without them sharing their data with each other, just with the clean room. And the way this works here is you've got Fabricam and Contoso. Fabricam sets up the clean room, invites Contoso, sets up tamper-proof contracts for what's allowed inside the clean room, sets up a key release policy that's also tamper-proof and attested, and then we'll execute the authorized queries, the ones authorized by that policy, into the clean room and obtain tamper-proof evidence that everything was adhered to, all the policies were adhered to. So in this case, neither Fabricam nor Contoso can see each other's data. And here's an example, very quickly, of a clean room where I'm going to upload an encrypted blob. That blob is encrypted to a key that will only be released to the clean room. Now we upload it. Let's go take a look in Azure portal at that blob, and you can see that it is encrypted, so the portal can't see it, Azure can't see it, only the clean room can see it. And this policy that we're looking at here for the clean room specifies that's where the data is and the policy for releasing that data. And then you can see this is where the output is going to go, again, with a policy for the output of that data. And now what we can do, just to show this in action, is execute two queries. One of them is a allowed query. So this is here from the governance, an approved query, which is going to query a Fabricam table and merge it with a Contoso table to get some user IDs. And we execute that query in the clean room, which it looks at, says this is an approved query. So and the output is approved to return to the whoever queries, encrypted to them, and then we're going to execute one that's not been approved. And you're going to see that when we submit that to the clean room, it's going to get rejected because it doesn't match the policy. So this, again, we're announcing the preview of this today. And this is the future of confidential collaboration and data sharing. You can imagine healthcare, finance, government, lots of scenarios where it's very hard to share data today, but with confidential protection of that data, that can unlock the doors for people to be able to collaborate like they couldn't before. So that brings me to the conclusion of the talk. I hope you found this interesting, informative, enjoyed some of the cool under the hood stuff that I showed you. And for those of you that have been coming before, I think you can see every time you see this presentation, it's new stuff. Some references back to the things that I talked about were coming that are now here. And so this is just an exciting time to be in the cloud. And by the way, I only talked about AI there at the very end, if you noticed, so you're welcome.